Hello San Francisco. I'm really excited to be here at droidcon 2024, and today I'm going to present my talk. It's called Jetpack Compose, Drawing Without Pain and Recomposition. In my session, I want to present some advice I've discovered myself, which can help reduce the number of recompositions and memory allocations using Jetpack Compose in certain situations. And a minor spoiler, there will be some pain in this session too. So a few words about me. My name is Vitalii Markus and I'm an Android engineer at Floor. And droidcon speaker, this is my second time where I'm in San Francisco. This is the QR code to my Twitter. If you have any question, you can write me there. I have more than 7 years of experience, and I used to work in fintech and food tech, and right now I'm super enthusiastic working at Floor, where I joined almost 2 years ago. As a part of the Health Monitor team, we are responsible for some features, which I'll describe very briefly later. So the Flow application, we started as a period evaluation tracker application, but over time we started integrating new features that helps user daily. We have more than 300 million installs. The app translated into 20 different languages, and it has 65 million monthly active users. So we started integrating Jetpack Compose a little over 2 years ago. In the first year, we mostly experimented with the small features, but in the second year, we began writing more and more features into Compose. Currently, 40% of screens are already written with the Jetpack Compose. And right now, we are going to the Compose-first approach, meaning that all new features are done exclusively with the Compose. And I'm very happy that we've implemented our design system using Jetpack Compose. So what we've already done that is quite large and significant. We completely redesigned the whole main screen using Jetpack Compose, created a symptom panel where user can log their symptoms, moods, and other life events, and introduced a symptom checker feature. This feature is based on the various user data collected automatically and manually from the chatbot dialog and provides the match probability to one of the predefined conditions. On this screenshot, you can see that the user has a significant match for the endometriosis. And today we are going to discuss the recomposition very briefly, triggers of the recomposition, how to optimize it, how different clients follow the same approach. Also, I'll touch memory optimization a bit. And we likely have a conclusion at the end. So first of all, I would like to say thank you that this talk was inspired by two people, Filip Novak and Andrei Shikov. I attach links to their talk, so you can see them later. And also, it looks like we have something in common with the previous session, which is presented by Ekshai and Tasha. Could you please raise your hand who were at that session? Okay, great, a lot of. So I try to highlight the problem, but from a little bit different angle. So let's start from the Jetpack Compose. We all know that it's a new declarative framework that shows data on the UI. It consists of 3 phases: composition, layout, and drawing. And during the composition phase, we determine what we want to display, into the layout phase where we want to display, and into drawing phasing what we actually draw or how we want to display, And moreover, the layout phase itself consists of 2 sub-phases. It's measurement and placement. In the measurement phase, we calculate the size of our composable, and in the placement, we position them. So look at this code example. Here we use modifier.size, where we specify the element size during the composition. In the measure method, and the code that's rounded, it's executed on the measurement phase. And in the placement phase, we position our placeable, which was calculated previously. The drawing phase is quite straightforward, so we don't touch it right now. So let's discuss the trigger recomposition. Generally, recomposition occurs when state value changes or the function's input arguments are updated. So the state value can be changed from the UI, view model, or at any moment during any phase. We can even update data during the composition phase, although it's not recommended because it can cause an infinite loop. But Compose can also handle it. When data is updated, we go through the composition and all other phases again. And this new cycle is called recomposition. So if we open the article from androiddevelopers.com with the name Follow Best Practice, they recommend using 4 core principles. Remember, to minimize calculation, derive state off, to limit recomposition, and using stable and immutable classes. And also using lazy layout keys to recompose only changed item into lazy lists. These principles are just to remind you. I won't spend any time of them. Let's go to the first example. It's very simple. On this slide, we have a general button. And on the click action, we update the state. Based on this state, we animate alpha from 0 to 1.5 and vice versa. And on this line, we read the alpha value from this state with the modifier.alpha. And let's check the recomposition count. And as you can see, we have a lot of recomposition during the animation. So I think we already know it, that there is another way to achieve the same behavior. We can use graphics layer modifier. It does the same thing, but without causing additional recomposition. And so we can see that there is no recomposition at all. Why it's happening? If we open the documentation, it's written that this version is preferred for reading animated, frequently changing states. And in this case, we just update the layer property, which does not cause additional recomposition. And also, if you noticed, we're into the graphic scopes. So we read our state only in the drawing phase. So, but what's happening if we want to create the custom extension? For example, the alpha layer. That is just wrapper for a graphics layer, the composable function. If we run the video, we can realize that we have the same result as the previous example. This is because even we change the alpha during the drawing phase, we still read state into the composition phase as an input argument. So, does the phase where we read state affect the recomposition count? Yes, it looks like it is. So let's take a look at the different phases of Jetpack Compose to understand how and where we can read the compose states. On this slide, we read state during the composition phase. So we read here width and height. And so every time when we pass a value into a metered modifier or composable function as an input argument, we read this state into the composition phase. Here, there is some custom modifier height. In this case, we read the state into layout modifier during the measurement phase. Next, we create constraint with the minimum and maximum height, measure it, and finally we place it. So in this case, I want to highlight that the position and the size of the box are identical to the previous one. So here we read offset state into placement phase and apply it to a place function. Thus, we created a custom implementation of the modifier offset. And in the last example, we use modifier draw with the content. With this modifier, we draw a line above the content. And inside it, we read the state of the stroke width into the drawing phase and pass it to the drawLine function. So why is so important on which phase we read a state? Because usually when a change in state triggers re-executing of one of the phases, all next phases also will be re-executed. On this slide, you can see that the average time of each phase, and we can notice that the composition is the longest one. So if during the composition phase we read frequently changing state, the composition phase and moreover measurement, placement, and drawing phases also will be re-executed. However, if we read state into layout or drawing phase, the composition phase will be skipped and won't be triggered, saving time and improving performance. This is exactly what we observe in our first example with the alpha for a button. So let's return to our best practice. And as we know, there is a fifth point, like the defer reads as long as possible, that we just demonstrated in our example with the alpha. So let's talk a little bit regarding the deferred reading, so how it could help us. In this case, we have a foo1 function which has a mutable state, and every 500 milliseconds we increment a value. We pass the same value to the foo2 function, then to the foo3, foo4, and to the end foo5. As you can see, when the state is changed, all nested functions are recomposed. Although in fact, foo3, foo2, and foo4 function haven't changed anything. They just pass in a value to the next function. So what we can try to do? Let's try to defer reading in this case. So we can defer it in two possible ways. The first one is to pass a state directly and read it with value property. Or the second one, we can pass a lambda. But in this case, there is no any difference. It depends only on your preferences. When we run the code, we can see that the behavior remains the same, but the number of recompositions significantly decreased, especially for bar and buzz 1, 2, 3, and 4 function. They are not recomposed at all, because we don't read the input argument in this function. We pass it further, and so the function doesn't subscribe to changes of the input arguments, and compiler optimize it. So in our case, we read value only in the bar 5 and buzz functions. So that's why only bar 5 and bar and buzz 5 function and text function are recomposed. So this is the example of our fifth point. Let's go to the next example. Let's talk a little bit about height. In our case, we have a button, and on each click, we change the state from the expanded to collapsed. Based on the state, we change the text and the height of the element. We read the value with the modifier .height, and if we run, we can see that each click triggers one state changes and one recomposition. And I want to highlight that there is no animation. Let's try to add it. In this example, we just replaced if with the animate DPS state. Nothing else has changed. However, we can see that during the height animation, a large number of recomposition occur. Why does it happen? Because in this case, we read state during the composition phase. And we want to avoid it. Let's try to achieve it in a different way. But this requires a little bit more work. We can create a custom modifier height that accepts not just DP, but for example, state of DP. And let's check how it affects recomposition. The amount of recomposition has decreased significantly. Let's find it out. On the left, there is the source code of the original modifier. And on the right, our custom solution. As you can see, the main difference is that the library ones uses DP everywhere, and we uses state of DP. On this slide, we calculate a target constraint, and the library code reads DP, but in our case, we read states via value property. And this is the whole difference. But the most important thing is knowing at which stage we read target constraints. We read target constraint during the measurement phase, and measure scope only confirms it. It means that we moved reading our state from the composition phase to the measurement phase, thereby eliminating excessive recompositions. And we can achieve the same result writing, for example, another modifier that accepts lambda. But let's try to do it without custom modifiers. We can use standard instruments to achieve the same result. We can use layout modifier in our case, and inside this block we read height value, create new constraint with the minimum and maximum height, and place the element. And if we run it, we can see that there is no recomposition at all. So we moved again reading our height from the composition phase to the measurement one. And let's go to the third example. It's with the background. This example is also very simple. We have 3 different colors, a shade of red, blue, and purple. When we click on the radio button, we change the state and start color animation with the animate color state. Then we read the state into background modifier. And again, we see a lot of recompositions. Because we read the state during the composition phase. So let's try to improve it. The idea is to use the same approach that I've already described with the height example. We can create a custom modifier that accepts lambda, that returns color instead of the pure color. And in this case, we can reduce the recomposition significantly. But how does it work? The idea is quite simple. On the left part of the slide, there is a source code of the original background modifier. And on the right one, our custom solution. As you can see, the main difference is here that on the left, we're using pure color and brush. And on the right, we are using everywhere lambdas for color and brush. And this is only a single difference between 2 implementations. But again, the most important thing is knowing at which stage we draw the background. And in our case, it's rectangle. We draw it during the composition phase, and I think it's obvious. And draw scope confirms it. On the right, we read color value from the lambda with the invoke method during the drawing phase. And it means that we moved reading our background from the composition to the drawing phase, thereby eliminating excessive recomposition. So, as I mentioned, we can achieve the same result writing another modifier, for example, that accepts states. But we can also achieve it with the standard tools. We can use draw behind or any draw modifier. Inside the modifier, we draw a background. In our case, it's rectangle, but in your case, it could be any shape, any color, any brush, whatever you want. And if we check the video, we can see that there is no recomposition at all in our case. So we again moved reading our color state from the composition phase to the drawing one. So I want to return to our best practice slide, and especially to the last point. And I want to add a sub-point here, even changing phases. So it means that we can defer reading 2 different phases to improve our performance. So let's see how this approach is used by Jetpack Compose and some libraries. Let's look at a few examples. So the basic example is the offset modifier, which takes a value in dp as an input argument. When we click the button, we start the animation and it changes from the 0 to 100. And during the animation, we see a lot of recompositions because we read the state during the composition phase. So in our case, to optimize it, we can use the offset modifier that takes lambda as an input argument. And in this case, we can convert dp to our pixels here. And all operators, including the reading state, will be accrued into layout phase. So this is one of the several examples how we can avoid excessive recompositions. So there is no recompositions at all. So let's try to understand how it works. On the left part of the slide, there is a modifier that takes dp as an input argument and create offset node. The right one takes lambda and create offset px node. The first modifier uses dp, so we can say that it reads the state value in the creation time, which happens during the composition phase. Meanwhile, the second modifier and the offset px node takes a lambda and calls it during the placement or layout phase. So we again move in reading our state from one phase to another. So let's talk a little bit about Lottie. Do you use Lottie in your projects? Yeah, great. So we also use it. So on this slide, there is a composable function for Lottie animation. It takes a Lottie composition and a progress. It's a value from 0 to 1. To call the composable function, we have to create Lottie composition and animate it with as a state. This state contains a progress value which we pass to the function. So let's run it and see what's happening. So we can notice the significant number of recomposition practically on even animation frame. But I found something interesting. The number of recomposition is limited. When the animation completes one iteration and starts a new one, there is no more recomposition at all. It looks like that Compose caches them for optimizations. Honestly, I have no idea what is it and how it works. So if anyone has an answer, I would love to hear it. And the Lottie implementation under the hood is very simple. It creates a Lottie drawable, update the progress value, and draw on the native Android canvas. And everything is happening during the drawing phase with the modifier draw into canvas modifier. And based on this implementation, developers decided to improve the library performance, and they updated the API in the new version 5.520. Now the progress passed as a lambda argument. What does it give us? Let's run the video. So if we run the video, we see that there is no recomposition in our case. But why? So it's happening because we invoke this function during the drawing phase into draw into canvas modifier. Thus, we moved the read in our progress from the composition phase to the drawing phase. And should we do it every time and everywhere? It's a good question. But for example, if we create super simple example containing only one clickable button and click several times, what do you see? How many recompositions do we see in the layout inspector? So we can see that it's happening regarding 20 recomposition for every button click. And it happens because of the elevation. It's a composable function which returns state of dp, and the value is read during the composition phase. So in this case, I think I follow the common practice, and I'll tell you that please optimize only when it's necessary. because in the pursuit of the optimization, you can make the code completely unreadable. So let's go to the next topic. It's regarding the memory. In our app, we have a custom component that is called Shimmer, and it shows the loading progress for required components. The API is very simple. We just wrap the content into a box and set a custom Shimmer modifier. And let's try to implement it in the optimized way. So we create a custom modifier, and inside it we run endless progress animation from 0 to 1. Since we aim for a more optimized version, we want to use like draw with cache function. Inside it, we create a brush, and we know that it will be cached, and we draw a rectangle over the content with the specified coordinates, size, and brush. For testing, I used purple and green to make the gradient more visible. But if we run the animation, we see that something happening that we cannot understand. The green stripe moves, but the purple one doesn't. So something is wrong with our implementation. The problem is happening because we only move in the rectangle, but we also have to move brush coordinates. And as a result, we have to recreate every brush when StartX value changes. So in this essentially roll back all benefits using the draw with cache modifier. And let's check the memory allocation. If we open the profiler, we can notice that during the Shimmer animation, the linear gradient from Compose was created 1,363 times. And the native Android linear layout was created the same number of times. It appears that we create a lot of items during the drawing phase. So we create the new brush for each frame of animation. So we can optimize it. And my idea is using the method which appeared in the first API of Android, canvas translate. It moves the canvas to the new coordinates and allows drawing the same elements and the new coordinates without changing any logic. With the translate method, we can now cache the brush and just call draw rectangle inside the translate block, where we move canvas for a StartX value. This solution provides the correct behavior and saves memory in our case. Let's check how its solution affects memory allocation. And as you see on this slide, there is only one instance of the linear gradient was created from the Compose. To be honest, I don't know why we have 3 instances of the native Android linear gradient, but it's much lower than it was before. So I'm quite satisfied with this solution. But there is another way how we could implement the Shimmer. For example, we can use offset modifier with the lambda. And this modifier is executed during the layout phase, unlike the previous solution, which was executed during the drawing phase. And as you remember from the previous slide, drawing phase takes less time, so the previous solution is still considered as more optimal. So let's go to the last example with the particles. So these are the 2 screenshots of our app. The left one, it's old design, and it was implemented with the native Android views. And the right one is the new design, which is fully implemented with the Compose. I think you see the particle system animation on the both frameworks, or we call it in the company spoiler animation. Let me explain how we've implemented it and the challenges we faced during the implementation into Compose. In fact, the particle system is built on a single principle. Every X milliseconds, the coordinates of the particles are recalculated, and all available particles are drawn with the new coordinates. And on this slide, we have the particle system class with the draw method that is called the internal implementation. We pass the bounds of the area where particles should be displayed, And a lambda argument specifies the emitter function that is responsible for a drawing. The function draw particles called native canvas draw points and pass their float array of the coordinates and the number of particles to be drawn. If we want to re-implement the same stuff with the compose, we need to write a method which works with the draw scope instead of the canvas. And fortunately, compose had the same method and it has the same arguments. So we again create a wrapper method for a particle system. The single difference is here that instead of the canvas and rect, we're using draw scope and compose size. And on this slide, there is the source code of the composable component. We have a particle system, and in the launch effect, we update the current time every 33 milliseconds to achieve 30 FPS animation. And then we call a draw method and pass the draw scope as a main parameter. And let's check how it affects memory allocation. After analyzing the profiler, I noticed that more than 79,000 of offsets were created during the animation. Why are these such huge numbers? Where do these values come from? We need to figure it out. Firstly, let's open the source code of the offset class. Offset is a mutable value class where x and y coordinates packed into a single long primitive type. It means that theoretically there shouldn't be any memory issue in our case, because all primitives are created not into the heap memory. But there is one stuff that is called boxing. If we check the source code of our draw points function, we can notice that the points argument is the list of offset. That's why the extension method toPoints return list of offset, which is delegated to the draw points method. And as you know, any primitive or value classes which is used or passed to the method at the generic type, and in our case, list of t is a generic object, all primitive and value classes will be boxed. So for us, it means that on every frame of animation, we create a new list with the new offsets and pass it to the draw points method. That's why we have a lot of memory allocation in our case. To optimize performance, it would be nice to use the same float array with the coordinate which is used for the native Android implementation. Fortunately, there is a solution. You can access to Compose Canvas through Draw Context. The Compose Canvas has a method called drawRawPoints, which directly accepts float array. However, there are some issues. This method ignores the important parameter, the number of particles to be drawn. Therefore, if an array contains elements with the 0 coordinates, the drawRawPoints will draw them. So keep an eye on these points. This is a lot of points with the coordinates 0, 0. And if we run the animation, we see that in the first time when we create the array, it contains the several elements with the default coordinates. So we decided to go in a different solution, which I would call a life hack. We can get an access to the native Android canvas from the Compose canvas with the embedded extension. As you remember, Lottie does the same thing. And in this case, we completely reuse the same logic without creating any additional methods working with the Compose. However, this solution has a drawback. It's not a multi-platform, unlike the previous one, where we work with the Compose canvas through the interface. And in the future, I hope that the Compose canvas method will be extended to support the number of particles. and it will be the same as the native Android API. So at the end, we repeated some stuff regarding recomposition. We got the approach how we can avoid excessive recomposition to moving, with moving the reading our states from the composition phase to the layout or drawing. And we got some life hacks how we can decrease memory allocation when you draw on canvas. So thank you for your time. Draw smartly and without recomposition. On this QR code, in this QR code is linked to the GitHub, and I promise that I push my test project there today or tomorrow. I don't know exactly. Yeah. Okay. Thank you.